Hi all, happy online lesson day today. So today I'm going to teach you about sections 2.5 and 2.6 of your textbook. This is about linear regression using two quantitative variables. Before you get started, what I want you to do is click on this link in your notes to watch the video by Hans Rosling. He is interested in public health and his website, gapminder.org, we're going to kind of refer to a number of times throughout the semester, but I think you'll find it very enjoyable. So when you click on the link, this is what you'll find, and I'm not going to play it completely right now, but that's what you're going to watch. It's a 4-minute video on visualizing 200 years of data about 200 countries where the two variables that Hans Rosling are interested in are income and life expectancy, and I think you'll find it very interesting. I'll come back to that later, but for now, let's go to the notes. So if you recall, we've talked about this phrase quite a bit. Correlation does not imply causation. So we're going to be looking at two quantitative variables. On the x-axis, or the horizontal axis, we call that in statistics the explanatory variable. And the vertical, or y-axis, is what we call the response variable. So we're trying to say that something on the horizontal may be able to explain what's happening with whatever is the variable on the vertical axis. So this is a silly example, but it is the explanatory variable's chocolate consumption in kilograms per year per capita around the world. And on the vertical, it's Nobel laureates per 10 million population. So this is saying that if you notice, the more chocolate consumption that there is seems to correlate pretty well with the number of Nobel laureates per 10 million people. So for example, Switzerland has the highest chocolate consumption and also the highest number of Nobel laureates per 10 million population. Whereas if you notice, China and Japan and Brazil are some of the countries that have some of the lower amounts of chocolate consumption, as well as fewer numbers of Nobel laureates. And if you kind of can use your eyeballs, you can imagine a straight line cutting through, averaging this right here. And that would be where we take a scatter plot of x quantitative variables and y quantitative variables, and we plot them all, and we see if there seems to be a trend. And I will explain what both of these numbers mean in the future. The r we're going to talk about today in class, r equals 0.791. Later on we'll talk about p in future classes. So, scatter plots and correlation. Interpreting scatter plots, you look for overall patterns or you look for outliers. You're going to be describing them in terms of direction, form, and strength. The direction is either positive or negative. So as we go back, if you look, the line is going up to the right, so that seems to be a positive direction. If it had been going down to the right, that would be negative direction. So think about your algebra slope. So there's positive direction, negative direction, or no clear direction whatsoever. The strength is strong, moderately strong, weak. We'll get to those categories in a minute, how we can describe them. So for example, if you look at this actually did come from gapminder.org. Again, that's where you'll find the video for Hans Rosling. But this is measuring number of children per woman. Basically, that's what they're calling total fertility. And the year is 2011. And on the vertical axis, the response is life expectancy in years. And if we eyeball it to look, there is an overall linear trend going downwards to the right. So that would be negative direction or negative association. And you can see that they all cluster right around this line right here. So the trend is that as the number of children per woman increases, the life expectancy tends to decrease. So where the countries that have an average number of children per woman is 1 or 2, the life expectancy is up here between 70 and 80 years of life. But down here, for the countries that have number of children is 5, 6, 7, the life expectancy is significantly less, around 50 or 55 years old. So this is a scatter plot with a negative association, and it looks pretty strong. All the dots cluster in a very close sort of straight line trend. The word we use is correlation. Correlation means that they seem to form this trend or pattern, and so we use the letter R. R is the correlation coefficient. R's have values between -1 and +1. Now, as an example, if we go back up here, this indicates that the R, the correlation between chocolate consumption and number of Nobel laureates per 10 million, is 0.791. Again, that's a value. 0.791 is a positive value between 0 and 1. So, back here, the sign indicates the direction of the association. If you basically have a value of 0, that means there's absolutely no association whatsoever. And the closer R is to +1 or -1, the stronger it is. So let's look at this scale. I've given you a scale that goes between -1 on this end to +1 on this end, with, of course, 0 in the middle. So on the left-hand side, everything between -1 and 0 is negative association. Everything on the right-hand side from 0 to 1 is positive association. Now, we're going to ignore everything on the left with negative association because we can imagine that everything will be symmetric to the right side once I talk about the right side. So halfway between 0 and 1 is 0.5. If your R correlation coefficient is 0.5, you have some weak association between your two quantitative variables. At 0.7, you have some moderate association. So I gave you a number like between 0.7 and 1. I gave you a number like 0.89. We'd say that is strong association, strong positive association. And something really close to 1, like 0.94, we'd call very strong association. So if we go back one more time to this, you can see that R is 0.791, which is moderate to strong correlation. Now, does that mean that eating chocolate causes a country to have more Nobel laureates? The answer is, as you would assume, absolutely not. That's ridiculous. But it does say that there is, in the countries that have more chocolate consumption, there does seem to be more Nobel laureates. And the real question is now, why is that true? And the answer is obviously not that chocolate consumption causes Nobel laureates to be produced in a country, but there's some sort of other factor that's connecting these two pieces that makes this thing correlate together, and we'll talk more about that soon. So always refer back to this correlation coefficient R scale when you need to. And again, I didn't discuss the negative because all you have to do is take these exact same values and throw the mirror image on this side to understand that a negative one would be a very strong association as well, just with a negative slope. And a negative 0.5 is a weak association just with a negative slope. So let's take some examples of, here are some numbers. So these are just some variables with quantitative variables associated with cars. And in the red in parentheses is your R correlation coefficient. So on the x-axis we have, or explanatory variable is city, miles per gallon. And on the y we have weight per of the car. And it's negative 0.91. Negative meaning negative association, and 0.91 being very strong. So there's a strong negative correlation between city MPG and the weight of the car, meaning that the miles per gallon increases as the weight decreases, which you expect. A lighter car is much more fuel efficient. Here we have fuel capacity and weight. So as the fuel capacity increases, the weight of the car increases, and that's a strong or moderately strong positive association. This is QTR, quarter mile, and weight, and it doesn't matter what those variables are. You see that the plots look like they're kind of all over the place. There is some sort of negative association. You can tell that because the value is negative 0.45, but going back to your scale, 0.5 is weak, negative 0.5 is weak. So negative 0.45 would be negative weak association. Here we have something very close to zero, so basically no association whatsoever between fuel capacity and the page number that you find the book in the car. I'm sorry, the car in the book. Quarter mile and acceleration in the first 60 seconds. That is a tremendously strong positive association, nearly 1.99. So almost perfect association between the quarter mile and the acceleration in the first 60 seconds. And then finally, the quarter mile and city miles per gallon is positive but weak association. You can see the plots are all over the place. And look at the distinction between these two plots. This is very strong association. They're nearly all lined up points, and here they're all over the place. Remember, correlation does not imply causation. So just because they're correlated does not mean that there was a cause and effect. So now we're going to actually look at linear regression, also known as least square linear regression. We'll just call it linear regression in this class. You've done this in algebra, so we just make a few little changes. So here we are. Linear regression models provide equations that relate explanatory quantitative variables to response quantitative variables. So here we have number of chirps of a cricket. So some scientist is counting the number of chirps in a minute, and they're also measuring the room temperature. And you can see that these points have a line that looks like it goes pretty well, that describes that as the number of chirps increases, the temperature in the room is also increasing. So A is the slope of the line. In y hat, we call this y hat, equals ax plus b. A is the slope of the line, and b is the y-intercept, just like you did in algebra, but you may have called it mx plus b. Okay, we are going to interpret the slope of a line. This is in the red box. This is really important because you will get quizzed on it. For each additional increase in, and in here you're going to fill in the blank of what the wording of your explanatory variable is. So for example, in the very first example, for every increase in chocolate consumption per kilogram per capita, and in this blank you're going to put the response value, the number of Nobel laureates per 10 million, and here we write increases or decreases. You choose this by whether your slope is positive or negative. So increases by, and then we need a number for the slope. This we don't have yet for the chocolate consumption, but we're going to do this with the examples. The only other thing you're going to need to learn is residuals, and we're going to do interpreting the slope and residuals in an example in a minute. But residual is what we call the prediction error. It's in this line, every point is either directly on the line or slightly off the line. It's either above or it's below. So how far off this point is from the line is the residual or the prediction error. So as an example, when we say residual is actual minus predicted, we take y, the actual data value, minus y hat, the prediction value. So I'm going to pause here. We're going to start a new video in a minute because we're going to run out of time to do this example.